Topic 5.3 is looking at bond enthalpies, and that is really where the energy is coming from when you are running a reaction, is from the bond breaking and bond formation. First, what is bond enthalpy? Bond enthalpy is the energy needed to break 1 mole of bonds in gaseous molecules under standard conditions. That is what we need to pay attention to here, gaseous molecules. We cannot easily break a bond in molecules that are in their liquid or solid state. And so we turn them into the gaseous forms and then break the bonds. That way we're breaking 1 bond at a time and a little bit more control. Average bond enthalpy is the energy needed to break 1 mole of a bond in a gaseous molecule averaged over similar compounds. So if you have, as an example, HOH, so you have a bond of O and H there, but you could also have C, and you have CH3, and then you have an OH for methanol. Well, due to this interaction of the oxygen and the carbon versus an oxygen and a hydrogen, that carbon's going to create a little bit more interaction between the oxygen and the hydrogen due to the pulling of the electrons and electronegativity. So we need to run an average of all different types of compounds that a bond could be in order to average how much energy it takes to break it. Bond breaking is an endothermic process. That means it takes energy to break bonds. And this is one of the biggest misconceptions in bonds. We think that when a bond breaks, that's how we get our energy. And for some reason, during digestion, that comes across in biology that, oh, food's being broken down and we're breaking up these molecules, so we're going to get energy from it. It actually takes energy to break a bond. Think about breaking a stick. Breaking a stick takes energy. So it is an endothermic process. Looking at this example, so we have Cl2, which is a Brinkelhoff, and so we do have a bond here of a Cl attached to a Cl. We are going to go through and we're going to break that bond into 2 separate chlorine atoms. The amount of energy it takes to break that bond is positive 242 kilojoules per mole. Another example. All right, so we have water, as I showed before, and we know that water has an H attached to an O attached to an H. We have to separate them individually. So first we're going to separate one of the hydrogens from the water. The amount of energy that takes is positive 502 kilojoules per mole. Then we still have this remaining OH, and we need to break that bond. And when we do that, we get a positive 427 kilojoules per mole. Therefore, you would think that when you have water, and water has 2 bonds with 2 H's attached to 1 O, we would take 502 plus 427, and we would get our grand total of positive 929. But that is for 2 bonds of the OH. So how do we know how much energy it average takes to get an OH bond broken? You would divide that by 2, and then you would get 464.5 kilojoules per mole. And that is how the average essentially works. This is going to be done in the gaseous state to reduce the effect of the IMFs to try to get just breaking that bond. And of course, this value right here that we calculated, it is going to differ, as I mentioned before, depending on where that OH bond is and how many in which you have to break. Something to keep in mind is when you have multiple bonds, and so that means when you have like a double bond or you have a triple bond, so an alkyne, alkene, the higher bond enthalpies and shorter bond, or the higher bond enthalpies and shorter bond lengths than single bonds. So it is easier to break a single bond because you only have to break 1 than it is to have to break 2 versus to have to break 3. And when you think about it, as you get more and more bonds, these atoms get closer and closer together. And you do have a table, a reference table in your data booklet representing the bond lengths. And you can make that correlation between bond length and the bond enthalpy it takes to break it. And as they get closer together, the stronger the attraction is between them. Bond formation is the exothermic process. So it's not when you're breaking food down that you get the energy. It's when you're converting that food into other molecules, such as if we're doing cell respiration, CO2 and water. So breaking glucose down into CO2 and water, you're actually getting a lot more energy. And we're going to touch base on that in a later topic, but because we're going to more simple molecules, more energy is being released during that process. So bond formation is an exothermic process. The same amount of energy is needed to break bonds as is given off in making bonds. So we are able to look at whether you're separating an OH or you're making an OH, it's either going to be positive or negative of the same number. So let's do some identifying. Which process is endothermic and why? Going through each of these. First, we have 2 chlorine atoms and we are making Cl2. So here we are forming a bond. And as we just saw, that makes this an exothermic process. Okay, looking at the next one, we have Na, and Na is separating into Na plus and an electron being removed. And so we are removing something here. Essentially, we are breaking apart that sodium. So if you are breaking, that is an endothermic process. Then we have a sodium ion and a chlorine ion, and that attraction forms your sodium chloride lattice. So that makes it exo. And lastly, we go from a sodium gas, so lots of energy with lots of sodium atoms floating around, to a sodium solid, so that means it's much more ordered. You are increasing essentially the bond attraction or the IMF attraction, which is a type of bond, right? So you are forming, which means it is an exo process. Therefore, our second choice is the one we are looking for. Where does this come into place? So calculating energy from bonds in a reaction. So again, we are going through and we are going to be calculating our delta H. Just like we had before. This is just another technique to go through and figure out how much energy is going to occur in an reaction. We have a reaction. CH4 gas reacts with O2 gas to make CO2 gas and H2O gas. As you can see, they're all in their gaseous state. So we can go through and successfully break the bonds individually and have little intermolecular force attraction. How we go about doing this? First, you need to know what kind of bonds are present. So you need to draw the Lewis structures for each of your compounds represented in the reaction. All right, so methane, we have our carbon, and there are 4 hydrogens attached to it. And we have 1 of those. We have 2 oxygens, and oxygen has a double bond between them. We have 1 carbon dioxide, and so we have an oxygen double bonded to a carbon, double bonded to an oxygen. And we have a water. If you do not remember how to draw Lewis structures, make sure you come see me for help, because if you draw the wrong Lewis structure, the entire work and the entire problem is going to be gone. So you have 3 to 4 points that you could potentially miss by drawing the Lewis structure. All right, so now I'm going to go through and identify how many bonds I'm actually working with. So seeing in this methane molecule, right, we have 1, 2, 3, 4 carbon hydrogen bonds. So I'm going to write that right below it. So I have 4 carbon hydrogen bonds. Okay, if we look at the next one, we just have 2 atoms, so we just have essentially 1 bond represented. So we have 2 O double bond O. And then if we look at carbon dioxide, we have 1, 2. So we have 2 C double bond O. And then let's look at water. So we have 2 OH bonds in water. We have 2 waters present. So we have a total of 4 OH bonds. Okay, so now, when you are breaking a bond, it is an endothermic reaction. So the values are going to be positive. When you are forming a bond, it's an exothermic reaction, so your values are going to be negative. The values you need to solve this problem are in section 11 of your data booklet. And it is a table with lots of different, essentially a lattice table that you have to go through and read and figure out where, which bonds you're using. By no means is this comprehensive, but if it's not in this table, it will be given to you in the question. So if we reference table 11, and I know I have 4 carbon-hydrogen bonds, that means I have 4 times a positive 414 kilojoules per mole. I have 2 O double bond O, and that value is going to be positive 498. Looking at the reference table 11, you're going to see all the values are positive. That's because, as we said before, the same amount of energy to make and break, they're the same number. You just have to put a positive or negative if it's forming or breaking, so on and so forth. So now we have 2 C double bond O's. If you look, C double bond O has a number of 804 in table 11. But because it's being formed, we need to change that to a negative. So it's negative 804. And lastly, we have 4 OH bonds. And again, you're going to see that the OH bond has 463. Because it's being formed, it becomes negative 463. So then we go through, and for our breaking, we have a positive 2,652, plus our forming side has a negative 3,460. And so our grand total difference is 808 kilojoules per mole. So that means this reaction is an exoreaction, an exothermic reaction. That means the bonds formed are going to be stronger than the bonds broken. And we're going to expect energy to be released in this overall reaction, which makes sense because what type of reaction is it? We go back and look, and this is a combustion reaction. And we know all combustion reactions are exothermic, and now we have just proven that it is exothermic. So when you go through and do this, these can be anywhere from 3 to 4 points. Each step I wrote down is a point they'd be looking for. All right, so they may or may not look for one of either the Lewis structure or just representing the bond. So that is one potential point. All right, then they're going to see to make sure you correctly identify each side of breaking and forming, and then of course the correct value with the correct units. Ozone depletion is a new topic to energetics topic 5, and it shows us where and how we can use bond enthalpy and energetics to help us understand some of the phenomenon we see. So the atmosphere goes from space to the surface of the Earth. And the closer you are to the surface, the warmer the atmosphere gets because the surface re-radiates solar radiation as infrared radiation. And infrared radiation is what heats us up. So we expect as we go further away from the surface of the Earth, we see a decrease in temperature until you hit the ozone layer, and we actually see a spike in temperature. And everyone at one point is wondering, why does this happen? Well, we can look at the breaking and forming of the ozone to see where an exo versus endothermic reaction is taking place. Also, this can help explain how different chemicals that we release in our aerosols can further cascade the breaking of ozone instead of the formation of the ozone layer. So looking at ozone, so in the atmosphere, we have oxygen, O2. And as we know, that is O double bonded to an O. with electron pairs. Ozone is O3. And here, so we have 3 oxygens bound to each other. Drawing their Lewis structures. And due to that double bond, we have delocalized electrons, or we have resonance. So that means that double bond could shift to the other oxygen. And it doesn't really matter. So if we look at regular oxygen, O2, we know we have 2 bonds between each of the oxygens. Ozone has 1.5 bonds because of the delocalized electrons between each oxygen. Therefore, it's a little bit weaker. So oxygen is stronger. And therefore, to break oxygen, it needs to be broken by higher UV light. UV light that has more energy. And so we can use this understanding of how much energy it takes to break O2 to make O3, to break O3 to make O2, and go back and forth by understanding how strong the bonds are between each of those oxygens. What is really neat about understanding radiation and bonds is you can actually go through and figure out what wavelength, what energy is needed to break a bond, so on and so forth, so we can really start to understand radiation. So we have this calculation. E photon equals H times V. E photon is the energy of essentially the radiation and how much radiation and what wavelength the radiation needs to be to break a bond. H is Planck's constant, and that is 6.63 times 10 to the negative 34th joules seconds. V is frequency. Now, when we're looking at radiation and we're looking at the electromagnetic spectrum, we have a calculation we need to work with, and that's C, which is the speed of light, equals wavelength times frequency. All right? So if we rework this, that we have frequency equals the speed of light over wavelength, all we know, because speed of light is a constant, H is a constant, and we know the wavelength of radiation, and that can be measured very easily. So we can substitute this information. So we have E photon equals H times the speed of light over the wavelength of light. All right, so if we know that the bond energy of ozone is 363 kilojoules per mole. Given that information, we can actually go through and we can figure out what wavelength of light breaks the ozone bonds. And that helps us understand. We can do this with O2, we can do this with Cl2, we can do this with water. And so we can understand the effect of radiation on any compound, which has numerous different applications. So understanding how we're going to work through this problem, you could solve for any bond that we have, as long as you know the bond energy for that compound. All right, looking at units first. As you can see, unit of energy is kilojoules per mole. Well, energy, if we go back over to our calculation, that's joules, right? Planck's constant is joules second. Speed of light is meters per second. Wavelength is meters. Nowhere is there moles, so we need to get rid of this moles. And so we are going to take Avogadro's number, or Avogadro's constant, times that by the energy of our photon. So we know that we have 363 kilojoules per mole, right? I'm going to change that to 363,000 and change it to joules so that it is consistent with all the other numbers we're going to be working with per mole. Divide that by Avogadro's number, 6.02 times 10 to the 23. Mole, we now get to cross out that unit. So we're going to take that information, we're going to plug it into our calculation. Okay, so we know what our E photon is. That's going to be the number we just calculated. We know H, we know C, we do not know wavelength. So I'm going to rearrange this calculation to isolate what we're looking for. What wavelength of light is needed to break O3? So when we rearrange it, that becomes wavelength equals Planck's constant times the speed of light over the energy of that bond. Let's go through and plug in our information. All right, so Planck's constant is 6.63 times 10 to the negative 34th joules second, times that by 3.00 times 10 to the 8th meters per second. Divide that by 6.02 times 10 to the negative 19 joules. All right, so that means joules cancels out, seconds cancel out, we're left with meters, we are good to go. So that is going to give us 3.30 times 10 to the negative 7th meters. That is not a fun number, right? So light is usually measured in nanometers when we're within the infrared, visible, UV spectrum, so on and so forth. And nanometers is 10 to the negative 9th as a reminder. So this is 330 nanometers. So this is the wavelength of UV light that can be used to break ozone. And so that's the one we have to keep an eye on. So how does ozone form and break then? Well, the formation and depletion of ozone, this helps explain why there's an increase of temperature at 12 kilometers above the Earth's surface. And so why we see that spike when we should have predicted a decrease all the way to space. You could do this calculation, but I'm not going to have you to. So O2 can be broken by a wavelength of 242 nanometers. So we just found that O3 can be broken by 330 nanometers. So those are the wavelengths of light that we need to understand. So if you look at O2, that's a smaller wavelength, which means it's a higher frequency, which is higher energy light. Therefore, it helps explain that the bonds in O2 are much stronger. Now this is called the Chapman cycle. And there are 4 steps here. Okay, so first, we have O2. Up in the atmosphere, O2 interacts with UV light at a range of 242 nanometers. When that occurs, you create O radicals. So that's O with a dot. That means each oxygen does not actually have a complete octet. And we call this free radicals. And they are very reactive because they want that full octet, whether they're going to give up an electron or gain an electron. So what happens is that free radical is like, dude, I'm not happy, right? He's going to interact with an oxygen hanging out right next to them. They're like, okay, we can make this work, and we're going to create O3. So here we've just created some ozone, and this is an exothermic process because we formed a new bond. So if it's an exothermic process, that means it is releasing heat to the atmosphere. Oh my goodness, once again, so increased temperature. So this helps explain why temperature increases at 12 kilometers, because this is where the UV light is interacting. In step 3, we now have ozone, and this is all kind of occurring at the same time. We've just broken it down in steps. So we have ozone, and it gets hit by 333 nanometers of light. That is going to create a free radical, oxygen, and O2 gas. Oh, we just made some O2, right? It's a cyclic process. Well, we just broke a bond, which means this is an endothermic reaction, right? So it actually took heat to break it in. So those first 2 steps kind of equal each other out. And so you're like, well, now we're back to square one, right? Well, we've got one more step. So we have another O3, and that O3 is going to react with an oxygen radical. And when this happens, you create 2 O2s. And because you're creating an extremely stable molecule, This is going to be, again, an exothermic reaction. There are more bonds present. So if we look, we have 2 exothermic reactions to 1 endothermic reaction. When this happens, because we have more exothermic reactions, we see an increase in heat in the stratosphere. Ideally, ozone formation equals ozone depletion. And that would be an ideal atmosphere. Well, what happens if something comes in and interacts with one of these areas and we stop ozone formation? And that means ozone depletion takes off. And that is what you look at when we see the ozone depletion, which we'll discuss further in class.